Quantum anomalies are like discovering glitches in this world's code, unexpected occurrences that defy classical physics and challenge our intuition. One example is the quantum Hall effect. Normally, when electricity flows through a conductor, it encounters resistance, like friction slowing down a moving object. However, in the quantum Hall effect, under specific conditions and at very low temperatures, electrons move in a way that seems to defy this resistance, flowing without losing energy. It's like cars driving on a road that doesn't slow them down. It's a quantum anomaly. Another example is quantum entanglement, where particles become mysteriously interconnected, regardless of the distance between them. If you change the state of one particle, its entangled partner instantaneously reacts, as if they're communicating faster than light, a phenomenon that challenges our understanding of space and time. Recent anomalies and discoveries in quantum mechanics continue to push the boundaries of our understanding and open new avenues for research and applications. Here are a few recent examples. Time crystals. In 2021, scientists at Google AI and Princeton University reported the experimental observation of time crystals. Time crystals are systems that exhibit periodic motion in their ground state without any external driving force. This phenomenon challenges conventional notions of equilibrium and has implications for quantum computing and quantum information processing. Mysterious electron behavior in high-temperature superconductors. Researchers have observed unusual electron behavior in high-temperature superconductors, where electrons seem to organize themselves into patterns not predicted by conventional theories. Understanding these patterns could lead to the development of new superconducting materials with higher critical temperatures, crucial for practical applications like efficient power transmission and magnetic levitation. Quantum supremacy. In 2019, Google claimed to have achieved quantum supremacy, the ability of a quantum computer to perform a calculation that is beyond the reach of classical supercomputers. This milestone, though debated, represents a significant leap in demonstrating the potential of quantum computers to solve complex problems faster than classical computers. Quantum friction and quantum thermodynamics. Recent studies have explored quantum friction, where quantum fluctuations can lead to unexpected energy dissipation mechanisms at the nanoscale. Understanding quantum thermodynamics, which deals with energy transfer and conversion in quantum systems, is crucial for developing efficient nanoscale devices and understanding fundamental limits to energy efficiency. Quantum spin liquids and topological phases. Ongoing research continues to uncover new topological phases of matter, such as quantum spin liquids, where spins interact in complex ways, leading to novel quantum states. These phases hold promise for future quantum technologies in understanding exotic behaviors in condensed matter systems. These recent anomalies and discoveries highlight the dynamic nature of quantum mechanics research, where scientists continuously uncover phenomena that challenge existing theories and pave the way for transformative technologies in quantum computing, communication, and materials science. In physics, we often rely on symmetries to guide our understanding of the universe. Symmetries represent a sense of balance and order, dictating that the laws of physics should remain the same regardless of certain transformations. For instance, the laws of motion should hold true whether you're standing still or moving at a constant speed. This principle of symmetry is deeply ingrained in classical physics, providing a sense of predictability and elegance to the natural world. However, as we venture into the quantum realm, we encounter a fascinating twist. Quantum anomalies, as we call them, represent unexpected deviations from these classical symmetry rules. It's as if the universe has a mischievous side, occasionally throwing us a curveball and challenging our preconceived notions. These anomalies are not mere theoretical constructs. They have been observed in experiments, leaving physicists both baffled and intrigued. But why are these anomalies so significant? Well, they provide us with crucial insights into the fundamental nature of the universe. Their existence suggests that there are deeper layers of reality, governed by laws that we are only beginning to grasp. Moreover, quantum anomalies have far-reaching consequences. They influence the behavior of particles, affect the strength of forces, and even play a role in the evolution of the universe itself. In essence, quantum anomalies are like cracks in the seemingly perfect facade of classical physics, offering us glimpses into a more profound and mysterious reality. By studying these anomalies, we embark on a quest to unravel the deepest secrets of the universe, pushing the boundaries of our knowledge and challenging our understanding of the fundamental nature of reality itself. The true hallmark of any scientific theory lies in its ability to withstand the scrutiny of experimental verification. No matter how elegant or mathematically sound a theory may seem, it ultimately must confront the reality of the physical world. In the case of quantum anomalies, the interplay between theory and experiment has been particularly fruitful, leading to a deeper understanding of these subtle yet profound phenomena. One of the earliest and most compelling experimental confirmations of quantum anomalies came from the study of neutral pion decay. Pions, subatomic particles that mediate the strong force, were known to decay into 2 photons. However, classical theories predicted a decay rate that was inconsistent with experimental observations. It was the inclusion of the chiral anomaly, which affected the way pions interacted with electromagnetic fields, that resolved this discrepancy. The anomaly predicted a slightly faster decay rate, bringing the theoretical predictions in line with experimental results. This successful explanation of a previously unexplained phenomenon solidified the status of quantum anomalies as not just theoretical curiosities, but as essential ingredients in our understanding of the quantum world. The confirmation of the chiral anomaly in pion decay was just the tip of the iceberg. Subsequent experiments, increasingly sophisticated in their design and execution, continued to uncover the fingerprints of quantum anomalies in various physical systems. From the quantum Hall effect, where anomalies lead to quantized conductance in 2-dimensional materials, to the study of black hole thermodynamics, where anomalies play a role in understanding the enigmatic properties of these cosmic behemoths. The experimental evidence for quantum anomalies has become overwhelming. To truly grasp the essence of quantum anomalies, we must first journey into the heart of the quantum classical divide, a chasm that separates the familiar world of our everyday experience from the strange and counterintuitive realm of the very small. Classical physics, the physics of Newton and Galileo, reigns supreme in describing the motion of planets, the trajectory of projectiles, and the flow of fluids. It's a world of predictable cause and effect, where objects have definite positions and momenta, and the future unfolds with clockwork precision. But as we delve into the microscopic world of atoms and subatomic particles, the comforting determinism of classical physics begins to crumble. We enter the domain of quantum mechanics, where particles can behave like waves and waves like particles, where uncertainty reigns supreme, and the very act of observation can influence the outcome of an experiment. It's a realm where our classical intuitions often lead us astray, and we must embrace a new set of rules to make sense of the subatomic symphony. At the heart of this quantum classical divide lies a fundamental difference in how symmetries are perceived. Classical physics holds symmetries as sacrosanct, inviolable principles that dictate the behavior of the universe. Energy, momentum, angular momentum. These quantities are conserved, meaning they remain constant over time, reflecting the underlying symmetries of the physical laws governing them. These conservation laws are not mere theoretical constructs. They have profound implications for our understanding of the universe, from the stability of atoms to the large-scale structure of the cosmos. However, the quantum realm throws a wrench into this seemingly perfect symmetry. Quantum anomalies, like whispers from the abyss, reveal that these cherished symmetries, while valid in the macroscopic world, can be broken in the subtle and ethereal realm of quantum phenomena. It's as if the universe, at its most fundamental level, plays by a slightly different set of rules. A set of rules where the familiar symmetries of the classical world can be subtly but profoundly violated. Imagine a perfectly symmetrical object, a pristine snowflake with its intricate six-fold symmetry. Now imagine a tiny imperfection, a slight deviation from perfect symmetry, almost imperceptible to the naked eye. This imperfection, however small, can have profound consequences for the snowflake's behavior. It might cause it to melt slightly differently, to fall at a slightly different angle, or to interact with other snowflakes in unexpected ways. In the quantum world, symmetry breaking plays a similarly crucial role, albeit on a far grander and more abstract stage. Quantum anomalies, those subtle violations of classical symmetries, act as the imperfections in the otherwise symmetrical fabric of the quantum realm. These anomalies, far from being mere mathematical curiosities, have profound implications for the behavior of particles, the interactions between them, and the very structure of the universe itself. One of the key consequences of symmetry breaking is the emergence of new particles and forces. In the early universe, for example, the fundamental forces of nature, gravity, electromagnetism, the weak force, and the strong force, were unified into a single, symmetrical force. As the universe cooled and expanded, this symmetry was broken, giving rise to the distinct forces we observe today. This process of symmetry breaking is thought to have played a crucial role in shaping the evolution of the universe, from the formation of the first particles to the creation of stars and galaxies. But symmetry breaking is not just a relic of the early universe. It continues to play a vital role in the quantum world. In condensed matter physics, for example, symmetry breaking is responsible for the emergence of exotic states of matter, such as superconductors and superfluids. These materials exhibit remarkable properties, such as zero electrical resistance or the ability to flow without viscosity, all thanks to the subtle breaking of symmetries at the quantum level. Quantum anomalies take us from the tiniest subatomic particles to the vast expanse of black holes, revealing a universe far stranger and more wondrous than we could have imagined. These anomalies, those subtle yet profound deviations from classical symmetries, stand as testaments to the enduring power of the quantum world to challenge our intuitions and reshape our understanding of the cosmos. Like cracks in a seemingly perfect mirror, quantum anomalies offer us glimpses into a deeper layer of reality, where the familiar rules of classical physics give way to the bizarre and counterintuitive laws of the quantum realm. They remind us that the universe is not a static, clockwork mechanism, but rather a dynamic, ever-evolving tapestry woven from the threads of quantum uncertainty and entanglement. The study of quantum anomalies has not only deepened our understanding of the fundamental building blocks of nature, but has also opened up new avenues of exploration in fields as diverse as condensed matter physics, cosmology, and quantum information science. These anomalies, far from being mere theoretical curiosities, have led to the discovery of new states of matter, provided insights into the evolution of the early universe, and even inspired novel approaches to quantum computing. As we stand at the frontier of quantum exploration, with new experimental tools and theoretical frameworks emerging at an unprecedented pace, the enduring allure of quantum anomalies continues to beckon us forward. These enigmatic rule breakers, like cosmic signposts, point us towards uncharted territories on the quantum frontier, where the most profound mysteries of the universe await our discovery. The study of quantum anomalies, far from being a closed chapter in the annals of physics, is very much a vibrant and rapidly evolving field, teeming with unanswered questions and tantalizing hints of new discoveries on the horizon. As with any scientific endeavor worthy of our curiosity, each answer we uncover only serves to deepen the mystery, revealing new layers of complexity and pushing the boundaries of our understanding. One of the most pressing challenges in the study of quantum anomalies lies in fully integrating them into a consistent and comprehensive theory of quantum gravity, a theory that would unify the force of gravity with the other fundamental forces of nature. String theory, a leading candidate for such a theory, offers some tantalizing hints, suggesting that gravitational anomalies might be canceled by the existence of extra-spatial dimensions, curled up at sizes far too small to be detected directly. Another exciting frontier lies in exploring the potential applications of quantum anomalies in emerging technologies, particularly in the realm of quantum computing. Topological quantum computers, for example, aim to exploit the unique properties of topological states of matter, which are intimately linked to quantum anomalies, to create more robust and fault-tolerant qubits, the building blocks of quantum information. The study of quantum anomalies also has profound implications for our understanding of the early universe, where the extreme temperatures and densities may have amplified the effects of these subtle symmetry violations. Cosmologists are actively investigating the role of quantum anomalies in explaining the origin of the matter-antimatter asymmetry, the cosmic imbalance that allowed matter to dominate over antimatter, giving rise to the stars, galaxies, and ultimately life itself. As we venture deeper into the quantum realm, Guided by the flickering light of quantum anomalies, we can be certain that the universe will continue to surprise and amaze us, revealing new wonders and challenging our preconceived notions of reality. The journey ahead promises to be as exhilarating as it is unpredictable, a testament to the boundless capacity of the human spirit to explore the unknown and unravel the deepest secrets of the cosmos.